Good morning, good day, and good evening, and a Happy New Year to all our attendees joining us for today's latest Data Science Central webinar. Before we begin, I would like to thank Altiscale for sponsoring today's event. Altiscale is a relatively new sponsor and supporter of the Data Science Central community, and we are honored to have them sponsoring our webinar today. I'd also like to take this opportunity to mention and show appreciation for some of our other recent sponsors, including MapR, Teradata, Tableau, Hortonworks, Pivotal, and Cisco, to name just a few. These past webinars are available on demand at datasciencecentral.com, and if you've not had the opportunity to view them, I would encourage you to take a look, as they do provide some very useful information. Today's webinar is entitled Practical Tips for Making Hadoop a Productive Environment for Data Scientists. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be approximately 1 hour long. We have a single panelist that I'll introduce to all of you in just a few moments. We should have about 10 to 15 minutes for Q&A following the presentation, and this event is being taped and will be made available later on this afternoon at datasciencecentral.com. I would also like to encourage our attendees to ask questions throughout the presentation. We will be reviewing them and presenting them on your behalf during the Q&A portion of today's event. My name is Tim Madison, and I am one of the co-founders of Data Science Central, and I'll be your host for today's webinar. I'm very pleased to introduce today's speaker, Raymie Stata of Altiscale. Raymie is the CEO of Altoscale, and prior to joining was with Yahoo, where he was the Chief Technical Officer. He also played an instrumental role at Yahoo in algorithmic search, display advertising, and cloud computing. He also helped set Yahoo's open source strategy and initiated its participation in the Apache Hadoop project. Prior to joining Yahoo, Raymie founded Stata Laboratories, which Yahoo acquired in 2004. He received his PhD in computer science from MIT in 1996. Thanks for being with us this morning, Raymie. We're looking forward to your presentation. In attempting to work on Hadoop-based data scientists face really two options that are neither really that good. One is to use Hadoop indirectly by engaging in a slow and error-prone back and forth with data engineers who translate your needs into Hadoop programs. Or second, to use Hadoop directly by using relatively unfamiliar and unproductive command line tools that are often difficult to master. Fortunately, a new breed of Hadoop-based tools is emerging, which helps to solve this dilemma. These tools allow you to build an environment for big data science, which is both self-serve and productive. In today's webinar, we will be presenting some concrete tips for building such an environment, as well as practical insights into the processes and systems that enable the rapid iteration required by big data practitioners, as well as their stakeholders. And before we begin, we have a quick survey that I'd like to ask our attendees to participate within. Just mark of the 5 selected options there, the one that best describes your current Hadoop environment. So if you just take a few moments to take a look at those, and just again mark the one that you think best describes where you happen to be with Hadoop at this moment in your organization. So I'll give you just another moment there, and then I'll progress the slides and we can all see the results. Okay, I'm going to move forward. Hopefully you all had a moment to check it off. Go ahead and quickly do so if you haven't done so already, and here we go. Here are the results. Thank you for participating. And with that, Raymie, I'm going to pass it over to you, and you can begin the presentation as soon as you're ready to go.
Great. Thank you. Well, I can see we've got an audience here mixed with people who have some experience with Hadoop and people who are just beginning to think about it. But I think the material we have to discuss today will be relevant to all of you. So thanks very much for joining. So here's a quick outline of today's presentation. I'll give a bit of a personal introduction, and then a quick problem statement, then dive into the meat of the presentation, which is sharing some lessons that we've learned here at Altoscale in working with our customers and creating environments for data science on top of Hadoop. Then at the end, we'll talk a little bit about Altoscale and our Hadoop as a service offering and how that might fit into the creation of such an environment. As far as I'm concerned, kind of riffing off that title, everything I needed to know I learned in kindergarten. For me, pretty much everything I know about data science I learned in the context of algorithmic web search. And I mention that because I think the experiences of the web search community, have been important in setting certainly the technology direction of Hadoop, and in other technologies that are used today for large-scale data science. I think one of the things to recognize about the web search in the early days is that, in the mid to late 90s, we didn't have the revenue of sponsored search. Today sponsored search, of course, is a big moneymaker, but back then sponsored search was still in the future. And so we had to tackle very large problems on relatively modest budgets. And this budget-constrained historical context, as I mentioned, had a huge impact on Hadoop. And it's both a strength and a weakness. I think the strength is that Hadoop allows you to tackle really large problems with relatively modest budgets. You don't have to have a government-scale supercomputer today to do supercomputer-scale problems. At the same time, a weakness of Hadoop historically has been that it's been a very rough environment to work in, and can be hard to use and unproductive for data scientists. So that's the primary issue that we'll be talking about today. So to sum up, Hadoop is great because it does provide a cost-effective platform for doing data science at scale. But it's not so great because raw Hadoop all by itself, is not a very productive environment. And historically, people have been faced with two bad options. Option number one is to use Hadoop directly, using unfamiliar and unproductive command line tools and APIs. And honestly, that's the approach we took in web search, where we expected our data scientists to be programmers, C programmers, Java programmers, as well as data scientists. And frankly, I think both those people and the people around them, like myself, were proud of the talent base we built up. But not every data scientist is a programmer, and that made it hard for us to access, a broader community of talent. The alternative, as far as using raw Hadoop is concerned, is to create a back and forth with a data engineer, where the data scientist would say, why don't you give me this subset of the data? And somebody will go off and get it and bring it back, put it in the workstation. It gets played with, and then you try again and again. And that, of course, is quite inefficient because you've got two people, misunderstandings happen, and there's a lot of latency there. The good news is, versus, again, those early days in web search, is that there's been a lot of development of tools that run on top of Hadoop that create a third way, a third alternative, where data scientists can go and do their work directly on Hadoop, while at the same time not having to use the raw Hadoop APIs to get their work done. So that's what we're going to talk about today, is this new generation of tools. They're really kind of been emerging over the last 5 years. And what we've done here is collect some lessons learned as we've worked with our customers in using these tools to create environments for data science on top of Hadoop. We've noticed some patterns in terms of how to get there successfully, and we've organized them, for presentation today. So, jumping right into tip number one, know your workflow. The goal here is to build a self-serve environment for data science. In such an environment, it needs to be engineered. That is to say, it needs to be purposely designed and built. And to do that, you have to understand your data science workflow in detail. Now, one point of commentary here is, in my experience, data scientists can sometimes be a bit parochial in terms of what is their role in the overall workflow, where they focus very narrowly on modeling, and their sense of ownership beyond that kind of degrades pretty quickly. I think a big part of the spirit of today's presentation is to have a bit more of an expansive view of what data scientists can do on their own in a self-serve fashion. And so in this regard, I think it's even more important to really think hard about what is the workflow and what is in the scope of the data scientists versus the people who they work with. That being said, at the end of the day, there are handoff points between the data science team and others. And I think when it comes to understanding and defining your workflow carefully, those handoff points also have to be considered very, very carefully because a lot of friction is often introduced at those handoff points. So what we have on the next slide is a common workflow that I've seen for doing data science on top of Hadoop. And I hasten to add here that this is for illustration purpose only for today's conversation. I think it's helpful to have a specific workflow up that we can talk about to make the points. Every organization, is different in terms of the problems that they're tackling, the data that they're analyzing, and also the type of talent that they've brought together. And I think all of those factors come together to create different workflows for different organizations. So the overall tip here, of course, is to think carefully about your workflow for your organization. But again, for the purpose of today's conversation, we'll use this specific workflow to make our points. Let me talk about some of the activities here in this diagram. At the core of data science is indeed what I call modeling. That can be finding regressions, doing categorization, building recommenders. There's that core modeling activity at the heart of data science. And so, of course, that's inside the workflow. But let me talk about a few of the activities that I've included here beyond that core modeling. In the context of doing data science on Hadoop, what I've noticed is that there is this process that I call flattening. Oops, sorry, my slide seemed to go backwards. Sorry, so we're on the slide talking about flattening. Sorry about that, folks. Anyways, back to flattening. So the issue here is that modeling tools, tend to take as input what database folks would call very denormalized data, right? Vectors and matrices where the values, are directly in the input records and not referenced indirectly. And at the same time, that's not a natural way to store the data for longer term purposes. And so there's this need to flatten the data. Very often the data is stored in Hive. And so, as suggested in this diagram, flattening can occur between Hive, and your modeling tool. But it doesn't have to be Hive. It could be HDFS files with JSON documents or whatever, again, your organization happens to do. But the flattening process is a very important part of data science because here often is where a significant portion of feature selection occurs. In putting together these flattened, denormalized inputs for your modeling tool, you have a decision in terms of, hey, how far out do I reach in my normalized data structure to pull in the attributes that I'm going to consider in my modeling process. In addition, there's an opportunity to create composite features, and this is often a very convenient place to do that. So you can take a number of different inputs from your normalized data and run them through a function, and have the output of that function be the attribute considered in your model. And indeed, that function itself could recursively be a model, right? You might have, for example, a classifier that looks at a bunch of attributes, and puts an input record into some kind of class, and then it's that class that's considered in your modeling process. So the flattening process is, an opportunity to do some, fairly rich activities in terms of the feature selection process. Now, what we've added to the slide here on the bottom, you might notice a few kind of loops that are nested. I put that here because, if you're, again, trying to define, or specify what your workflow is, I think it is helpful to think about nested loops of activity, where the innermost loop indeed is that modeling exercise, right, where you build your model and you test its accuracy. You build your model and you test it. You build the model and you test it, and that's the inner loop. But then, every once in a while you might say, hey, I'm not getting the performance that I need. And, to get the performance that I need, I have to rethink, what are the inputs that I'm taking in this modeling process. And so you pop out to an outer loop where you go through that flattening process again. and you pull in new data, or you create a new composite signal that might, be more predictive or, be more useful to your modeling process. And once you reflatten the data, you go back into your modeling tool, and you continue, you model and test and so forth. So there's these loops of activities. And there is kind of an outer loop that I've put here that arises very kind of commonly in the context of Hadoop that I've called exploration. And exploration arises because it's pretty typical in a Hadoop environment to, in some sense, store your data twice. You store it once in source form, so you've got the raw data as it comes in from, whatever the source of that data is. And that could be, again, XML files or JSON files or Apache logs or whatever. And you store for archival purposes that source form data. And then you go from the source form data, through a fairly aggressive transformation process, and then store the results of that into Hive. And the advantage of this two-step of storing it twice is that the transformation process indeed can be very aggressive. And you don't worry about, quote unquote, throwing away information or throwing away signals, because you've got the source form data and you can always go back to it if you need to. And the benefit of this is therefore the data in Hive, it's more structured, it's cleaned up more aggressively, so it's less noisy. It's smaller, very typically, so therefore it's faster to manipulate. So you've got this convenient Hive form of the data that's a little bit more highly curated, and then you've got the source form. If you take this approach, which is a very agile approach to exploring new data sets, what that leads to, though, is the need to occasionally go back to the source form data and to look for signals there that might have gotten dropped in your so-called aggressive transformation. And so that's where exploration comes into the picture. In many ways, exploration is like flattening, right? It's going kind of further upstream in the data and looking for signals that were lost. But unlike flattening, at least in the model that we're presenting here, it's done against far less structured data that's much dirtier. You haven't gone through a cleaning process to get rid of bad records and attributes and so forth. And frankly, data that's less understood. So, that is a slightly different activity. And again, you do that even less frequently, so that's the outermost loop of the process we've identified here. So this is an example, again, of a common workflow. It's not the only workflow on top of Hadoop, but we're going to use it to illustrate our other points going forward. So, once you have your workflow kind of laid out, in reasonably simple form, this is not, a very detailed specification. The next tip here is to go and look for where there's a lack of self-service. What we've done here is put circles around areas, where in our experience, there are problems. And again, your mileage may vary, but notice that we have not circled the modeling thing here. In terms of self-sufficiency, data scientists are typically quite self-sufficient in terms of modeling, both in terms of the tools and how to use them. So that's not a common problem area. But even in the context of flattening, I have noticed that that can be a problem area. Not always, but can be. There are environments where the Hadoop cluster is kind of off limits to the data scientists. It's considered quote unquote production, and therefore to get anything out of it, you have to go through some kind of data engineer by policy, which I think is not a very productive environment at all. But nonetheless, that you see that, so that's one reason why there can be a problem here. But even where data scientists are allowed to go directly to the Hadoop cluster, they often have to access it, for example, if they're using Hive, through the Hive command line tools, which are not very friendly. And furthermore, there's very often no data catalog, right? So they're kind of stuck trying to figure out what is all this mystery data, with weird table names and so forth. So even where there is a theoretical ability to be self-serve here, there's very often a lot of practical problems that prevent data scientists from being very agile when it comes to going and doing the flattening. And then as far as exploration is concerned, it's typically even worse. Where again, assuming that the data scientists can even access the Hadoop cluster, the source form data is very varied. Again, typically its formats aren't documented. But worse, to access it, you actually have to now write Java code, Java MapReduce code, for example, which is not an agile way to try to understand what's going on in your source form data. So those are some problems directly in the data science process. I've also circled some of the handoff areas. For example, in going from modeling to serving. Let's say that you're doing ad serving as an example. Again, it can be common for the data scientist to come up with a model and then hand that off to a software engineer who then translates that into C code, for example. And very often the performance of the model gets lost in that translation, and that creates a lot of problems. Down on the cleansing side, or a lot of people call that ETL, again, even if a data scientist has gone to the source form data, found an interesting signal, very often there's a team that owns the ETL pipeline, and they can have a very long backlog in terms of getting new signals through, creating a lot of latency. So again, another problem area, with respect to this flow. But again, the point is, not that these are the only problems that exist, or again, that this is the only workflow that's out there. The tip is, once you understand your workflow, to identify the problem areas. And so what we have on this next slide are a few signs to look for. One sign is data scientists, waiting on other teams to get their work done. It's not always the case that if a data scientist is waiting on another team, that is a problem. But my suggestion is, wherever you see that, have a skeptical eye. Say, hey, why can't data scientists do this themselves? Why are they waiting? And really kind of change your assumptions in terms of what is possible for data scientists to do on their own. This goes back to the spirit again of the point here, which is to say, hey, let's expand the scope of what can be done self-serve by data scientists. Again, wherever there are handoffs, to or from the data scientist team, always look at those carefully because there's typically friction there. And finally, even where data scientists are doing work themselves, if they're spending a lot of time kind of doing diagnostic work by doing searches on Google or looking at Stack Overflow, chances are they're using tools that are not adequate and not productive. And so again, that's another form of a problem to be solved. So at this point, you've defined your workflow. You've spotted the problem areas. Our next tip is to use best-of-breed tools to deal with the problem areas. Here, our point of view is that there is no single tool that's going to cover the entire data science workflow. So instead, as you look to put together this self-serve environment for data scientists, the mindset should be having a suite of tools that work together. And again, once you understand what your workflow is and where the problems are, that creates a very clear set of requirements for going out and finding tools that can help solve those problems. So it's not in the scope of today's presentation to kind of do an exhaustive survey of all the tools that are out there. But in the next few slides, we'll talk about a few tools, again, for the purpose of just illustrating, hey, how does this look like in practice? So we've thrown a bunch of logos up here, and so let us walk through these. Starting with flattening, again, my overall assumption has been that there is what we call the convenient form of the data stored in Hive, the aggressively transformed form. An implication there is that the data scientists will have to use SQL to get at that data. And I do think that data scientists should have reasonable familiarity with SQL for the purpose of doing flattening. Right? They don't have to be business analysts who know how to use complex windowing functions to do that kind of work. But you do need to do some basic joins to flatten your data. And so on the one hand, again, I think data scientists should be familiar with SQL. That said, as I indicated earlier, simply throwing folks into the Hive command line tool is not a very productive way to access Hive. And so what we have here are a couple of tools that run on top of Hive that provide a bit more of a user interface. On the bottom, it's hard to see, but that's a tool called Squirrel, which is a fairly venerable query builder for SQL, which can be used on top of Hive. We've also listed Hue as another possibility. That's an open source project that works specifically for Hadoop, and it includes a query builder for Hive. At Altiscale, we're actually working with a company that's currently in stealth mode, so we can't mention them, but they have a very innovative user interface for Hive, where not only do they use machine learning in the query building process, so that it makes almost eerily kind of good suggestions in terms of how to build your query, but it also goes through and it creates metadata or documentation around the data in Hive, so that you don't have to kind of look at the table name and try to guess what it means. Over time and through usage, documentation kind of gets generated automatically, which is really helpful. On the exploration side, there has been, again, over the last couple of years, a number of tools that have been developed that sit on top of HDFS and allow you to look at that without having to write MapReduce programs. At Altiscale, we've worked a bit with Trifecta as just one example. What's neat about that application is that it, again, will parse the data. It'll also do some data profiling, so you can kind of understand the frequency of different values in different fields. And it allows you to enrich the data. It allows you to spot anomalies or errors, and even build some rules to clean them out of the data. And then one nice feature is that you can push a button, and Trifecta will generate a pig script that will essentially do the transformation for you. And going back to that problem area that I mentioned earlier in terms of dealing with the ETL team, going to the ETL team with a pig script is very different from going to the ETL team with kind of a verbal explanation of a signal you want recovered from the data. And so, there is still an exercise of getting a change into production, but that can go a lot faster when you've got a very concrete piece of code that you'd like to be put into production. So that tool helps with that handoff as well. Over on the right-hand side, I've got a few tools listed around serving. I mentioned ad serving earlier, but ad serving tends to be a very custom type of serving, and so there's no ad serving tools, at least not yet. But another form of serving is having decision makers, right? It might be executives in your company, it might be your customers, interact with models, and playing kind of what-if scenarios around them. And again, in the past, the interface between the model and that ultimate user, let's say it's a customer, has often been people, right? Some type of internal analyst that knows how to take your model and then turn around and answer questions from another person. But what we've seen increasingly happen is that people are using visualization tools and plugging their models into the visualization tools so that the ultimate consumer, the people who want to do the what-if scenarios, can do those scenarios directly in the visualization tools. I would say that's still a little bit more early days on that, but again, a great example of moving to a much more, self-serve, reduced friction interface between the data science team, and outside consumers. So notice that, when we were talking about that Bestofbreed suite, I didn't talk about modeling. Here, that's a topic for a tip all by itself. Our tip here is to model directly on big data, directly on Hadoop. And again, just over the last few years, there's been a huge evolution of tools and the ability to do scale-out modeling directly on top of Hadoop. And so while understandably in the past, that's been a relatively rare thing, because using tools like Mahout, for example, it has been difficult and only worthwhile when there's a lot of benefit to doing so. But with these new tools, I think it's much more practical to move the modeling process off of workstations and directly on top of Hadoop. So we've listed a number of tools here that can do that. The tools on top are tools that are what I would call Hadoop native. So they're kind of starting from scratch with a specific eye towards being scale out, right, and working in that scale out big data manner that Hadoop, of course, is so strong at. On the bottom, I've got a couple of legacy tools listed. And what we see from the vendors of those tools is an increasing interest in embracing scale-out computations on top of Hadoop. And so that's another vector to this overall vision of modeling directly on Hadoop and directly on your big data. The alternative to big data modeling, as we're calling it here, is a fairly standard approach where you sample the data down till you can get it to kind of workstation size, and then doing your modeling on a workstation. And people have done that for so long. Sometimes you get questions. Hey, it works. Why bother? Why, if it ain't broke, don't fix it. And so I wanted to mention here what are the advantages of this new approach? Why change? And the advantage, I would say, is the combination of better accuracy achieved more quickly. On the accuracy side, if you have that big data modeling, you can deal with rare events, much more easily. You can deal with seasonality much more richly because you can just consider, more seasons and more data. More generally, you can manage the bias variance trade-off because you can consider both more features and more data. So you can reduce your bias, while managing variance more easily. So you can get better accuracy. Now, again, I think it's a bit of a religious debate as to whether, through enough sampling and ensemble building, you couldn't get to the same level of accuracy without doing the big data modeling. And the point here isn't to kind of weigh in on that debate, because I think the real point is that those kind of sampling processes they're very time-consuming and labor-intensive. And so if you don't have to do them and you can get more quickly and directly to your result, you just save a lot of time and you can iterate a lot more. So the higher level message here is that this new generation of big data tools are very cost effective. That's the overall theme of Hadoop, is cost effective processing of very large data sets. And I think they have changed the equation in terms of what's possible in big modeling. And we're getting to the point where people can start to change their practices as a result. So the final tip here is to create a help desk, even as you create this self-service environment. And I think this is extremely important complement to everything else that we've said so far. The point is, a self-service environment does not mean that you're totally on your own. And in particular, as I mentioned earlier, data scientists shouldn't be spending their time on Stack Overflow trying to figure out what obscure stack traces mean. And the reality of Hadoop is that certainly at the Hadoop level, and even the tools that I've been talking about that sit on top of Hadoop, as one example of many in Felicity's, they do report errors in the form of stack traces. And worse, those stack traces are often buried in log files. And typically developers are a lot better at interpreting stack traces than many data scientists. And I think a productive environment, does include getting help, from those experts, typically from developers, who, when something goes wrong, can come in, can say, here's what happened, you've run out of memory or whatever, and save what can be sometimes days of investigation to just get, one modeling run through. So having that kind of help around, I think, is important. At the same time, the goal should be, teaching people to fish, right? The goal should be getting to a point of self-sufficiency. One way that you can do that is to build a knowledge base, because very often, these difficult problems, or they're just kind of intricate problems, they tend to repeat themselves over and over again. So if one member of your data modeling team has a particular kind of out-of-memory error, chances are other people who are doing similar work are going to see the same problem. So if you have a developer come in and help you once, or an operations person, and you can somehow capture that in a knowledge base, then you don't get stuck on the same problem over and over again. And that makes the utilization of these experts, or what we call the help desk, very scalable. I think another part of helping people be self-sufficient is to instrument the diagnostic information that comes out. As I indicated earlier, a lot of the diagnostic information is buried into log files. And to make matters worse, these log files, are scattered all over the Hadoop cluster. Some get stuck on the slave nodes. Some are on these gateway machines where jobs are launched. Some can be kind of stuck, in workstations. So having tools that can kind of gather up or in some way search all of this different data, perhaps weed out the noise to help users more quickly get to the information to help them diagnose their problem, that's another valuable way to help people help themselves in this environment. So that's the end of our tips. What I want to do here in the last few minutes is to spend some time talking about Altiscale and what we do and how that fits into this vision of a self-serve environment for data science. So a little bit of a corporate background. We're soon to be a 3-year-old company. Many of the folks in the early days, came from Yahoo, myself included, where we were very deeply involved with Hadoop in the context of algorithmic web search, as I indicated earlier, and also various advertising and eventually mail and even media and everything we did at Yahoo. And applying data science at scale was a big theme of what we did at Yahoo with Hadoop. And we're fortunate to have a number of people from Yahoo who joined us, and share that vision of doing data science at scale. In many ways, the mission of Altoscale is to take the lessons learned, not just at Yahoo, but at Google and Netflix and LinkedIn and other web scale companies. And we have people from all of those companies. Take the lessons learned in building environments where people can do web scale data science and package that up, into a service offering that's easy to consume. What do? We deliver what we call true Hadoop as a service. It's the industry's first purpose-built petabyte-scale Hadoop cloud. And the key point here is that Altiscale operates Hadoop for you. We deliver HDFS, the Hadoop file system, Yarn, the Hadoop computing fabric, and also Hive as complete turnkey services. If the name node, for example, in HDFS goes into safe mode, that's our problem. It's not your problem. It's not the problem of your operations team. We take care of it for you with an SLA. So having that kind of highly reliable, strongly supported environment, I think, is foundational to having a productive Hadoop-based environment for doing data science. And I think that what Altiscale offers in terms of operations is particularly valuable for data scientists. I have seen a few companies where data scientists are actually expected to operate Hadoop themselves. And of course, while it's possible and some people figure out how to do that, it's certainly not using data scientists for what they're best at. But even where there's an operations team that will run an internal Hadoop cluster, often that operations team is responsible for a lot of different things. And dealing with problems in the data science Hadoop cluster, is often not their top priority. And so data scientists can get stuck kind of waiting, for issues to be dealt with, even in the context of a internally supported Hadoop cluster. At Altiscale, all we do is support those Hadoop clusters, make sure they're running well, deal with issues right away. And that allows our users to really focus on getting their data insights, and not with wrestling with Hadoop. A quick comparison of Hadoop as a service, which is what we do, to other forms of consuming Hadoop. One form is to go to an infrastructure service provider like Amazon, get a bunch of virtual machines, run Hadoop there. So that's the middle column. Or you can, get a bunch of machines yourself on-prem and run Hadoop on those machines, perhaps with a vendor like Cloudera helping you. So these are kind of the 3 common ways that you can consume Hadoop. And as you can see, a Hadoop as a service provider, offers a lot of value. First and foremost, as indicated earlier, in setting up and operating Hadoop, and also keeping it up to date. If you think about those modeling tools that I mentioned, those scale-out modeling tools, they're all dependent upon the latest and greatest from the Hadoop community. And so if your Hadoop cluster isn't up to date, you're not going to be able to access, the latest versions of those tools. One of the nice things about a Hadoop as a service offering is you do get the benefits of running on infrastructure optimized for Hadoop. That delivers not only performance benefits, but also reliability benefits. It can be really frustrating when your jobs are failing all the time because they're not on tuned infrastructure. And so that can bring a lot of productivity benefits to users. It's important that your Hadoop cluster be set up in a very standard way if you're going to be taking the approach outlined in this presentation. The tools that we talked about all kind of assume a standard deployment of Hadoop. So if you want to use those tools quickly and easily, you need to have that kind of standard deployment. Finally, as we have on the bottom, the Hadoop help desk is, I think, important for users who want to be more self-sufficient. And at Altiscale, we're very proud of the fact that we do have that help desk. We don't take a guilty until proven innocent, kind of mentality to people who come to us with problems. We really try to help our users be productive in building their models or doing their analyses, and get the headaches of Hadoop out of their way as quickly as possible. To be a little bit more concrete about Hadoop at Altiscale, in the bottom in the big blue boxes, there's kind of the core product, which, as I mentioned earlier, is the Hadoop distributed file system, the Yarn compute fabric, and also Hive, which is a SQL engine that runs on top of HDFS and Yarn. In addition, we have our help desk. And together, those are the core. But as you can see in the gray boxes, we are set up and we do support a wide variety of tools that run on top of that. There are tools like Oozie, for example, and HCatalog that are much more developer-oriented. There's tools like Trifecta, is one that we mentioned, which is good for both business analysts as well as data scientists. But also there's a lot of tools specifically for data science that we or our customers have run on top of our environment, including some of the ones mentioned on the earlier slide. So that's some of the concretes. How does it work? It's pretty simple. You get your data in to Hadoop via any number of transfer mechanisms that we've created. Then you access the Hadoop cluster using the tools that match your needs. This is a screenshot, I believe, of H2O. And then finally, we do have a self-serve portal where users can go to look at their job status. They can add colleagues or remove them from the cluster, so they can do some self-serve user management. And it's also through the portal that you have access to our help desk. A little bit of praise for Altiscale, and I won't go through all of it, but to kind of focus on the top left, what we see here, and I think what we've seen more generally, is that a lot of Altiscale customers are customers that are Hadoop veterans. And what they've learned is that the complexity of running Hadoop never gets easier, especially, again, in the context where the Hadoop software is evolving so quickly, and it's so important to stay up to date. It can be a serious burden to run Hadoop well. And even when people have somehow conquered that, they realize that effort is really not core to the value they deliver to their customers. And so by outsourcing to a Hadoop as a service provider, they can repurpose their best people to activities that are much more core to the value they deliver to their customers. So in concluding here, I do have a final tip. Oops, we've gone too far. There we go. My final tip for data scientists is to become an advocate. And I kind of alluded to this earlier on in the talk, where I said that while data scientists do feel ownership over their modeling tools, their sense of ownership often degrades very quickly as you get beyond that core modeling part of the process. As a result, they often accept the workflow and the tooling that's handed to them by others. They take it as kind of unquestionable, no matter how suboptimal it is. And frankly, no matter how unempowering it is in terms of, no, you can't go in the Hadoop cluster, just tell us what data you want and we'll get it for you. And I think it's important for data scientists to think more broadly about, what kind of environment would make them productive, to educate themselves in terms of the tools that are out there, and how those tools can help them be more self-reliant, and then become advocates for a self-serve Hadoop-based environment that's productive and reliable and, frankly, fun to use. That should be a first-class goal. So with that, we're done with the formal part of the presentation and can take some questions.
Great, thanks, Raymie. Great presentation. So we are at the Q&A portion. I have the current slide up with Raymie's email address, so you all can take that down if you have any questions following today's event. And during this Q&A portion, please continue to ask any questions that you may have. So Raymie, the first question we have for you is, can you talk a little bit more about the production cleansing process, please?
Yeah, so the production cleansing process, many people call ETL, extract, transform, load, where, again, data comes in, from a web server, or extracts from a SQL database, or, say, FTP dumps from customers. And that data is often, it's in whatever format it's in. You often can't control the format. There's typically certain noise levels or error rates in the data, and that data sometimes will have references to other data, right? There might be a customer ID in the data, but there's no information about what is that customer. And in fact, the customer ID might be from a key space that is, not the standard key for customers. So that's the data as you receive it. And then what the ETL process does is then it transforms that data. So it deals with the errors. And it's, from a data science perspective, dealing with the errors is really pretty critical. And that's why I chose to say production cleaning process, because I was emphasizing that aspect of dealing with errors. But of course, the transformations are equally important. And also remapping, for example, some of these keys to a more standard key space, so they're more easily dereferenced, is another thing that's often done in the ETL process. And so that's what that process is. And again, in the methodology that I've outlined here, historically with data warehousing, there was a very waterfall-y approach to this, where you would try to define a target data model that would solve all problems in the universe. And then you would build kind of an ETL process once and for all, that would get you to that. And of course, those processes were very long, consumed a lot of time, and typically would fail. So I think in the new world, people have to be thinking much more agilely, where you've got a particular problem, you do ETL for that problem, you learn more about the data, and you evolve the ETL pipeline in a very agile fashion over time, as you learn more and more and more about both the data itself and the problems you're trying to solve.
Okay, very good. Connected to that question and relative to sort of the tools, we have a few questions about, are there tools that you would recommend or suggest using for that process? Yeah,
I will say it's interesting that people are kind of highlighting that, because with respect to the overall spirit of this presentation, which is to say, hey, data scientists should be more self-serve, I think that is a problem area that, to date, is less than fully solved versus some of these other ones. I think that, as I indicated, a nice thing about a tool like Trifecta is that simple transformations and simple cleanup rules can be developed by data scientists directly, and then the result of that can be handed off in the form of code to a production ETL team. And so that's one particular tool that I mentioned. But that then does have to be plugged into an ETL process. There are tools like Kettle, which is an open source ETL system, Talend, Informatica, and then people do use Pig, together with Oozie as another way to build an ETL pipeline. So those are the types of tools that are in the core of of ETL. But I will say those aren't particularly self-serve for data scientists. So the model of Trifecta, I think, is kind of nice, where the data scientist can hand off a module that gets plugged into those other kinds of tools.
Okay, very good. Very thoughtful response to that question. The next question is, can we use Revolution R for exploration and SAS VA for serving?
As I mentioned earlier, I think every organization is unique in terms of the problems that it's trying to solve and the requirements. Using SAS VA for ad serving, as an example, is not practical. At the same time, if you're trying to do what I call the supporting the decision makers through what if scenario exploration, then that might indeed be a fine tool for doing that. So again, you need to look at your specific requirements to see what works. With respect to using R for exploration, and in general trying to make tools like R or SAS, be the one and only tool through which you do everything, I will say I would watch out for that mindset. Again, and this is an opinion based on a little bit of experience. I would suggest really embracing a best-of-breed approach, where there are indeed different tools, that are optimized for solving particular problems, found in your organization.
Okay, very good. So this question discusses sort of the skill sets of the data science. So understanding that a data scientist isn't necessarily a software engineer, they do need to have some fluency and skill set with software tools and languages. Can you recommend some software skill sets and tools that a data scientist should otherwise be competent with?
Sure. I've mentioned one already, which is SQL. I meant to say kind of fairly directly to those who only want to work in SAS and R that, hey, look, you got to know at least a little SQL if you want to work on top of Hadoop. So I would put that on the list for sure. Although again, I think there are query builders that can be used that can make that possible, and also I think there's a subset of SQL that's helpful for flattening. That is really the core data science toolkit, if you will. So that's one. Python is another language that I would suggest learning just for the sake of learning it, even if your organization isn't using it. And Python does get used by a lot of data scientists. I think that's more because there's some great libraries out there for doing data science in Python versus there's anything magical about Python versus, say, Ruby as a scripting language. But I think by learning Python, and becoming familiar with the libraries that are out there, you will just become a little bit more familiar with what it's like to actually use a programming language, and that will serve you well at some point in the future, even if you don't need that today. So I would put that on the list of things to learn. If your organization uses Hadoop a lot, and your developers, say the people, for example, who are working on that ETL or production cleansing pipeline, tend to use Pig a lot, then it might serve you well to become familiar with Pig. And so that would be another recommendation, though, again, I think that one is much more situational. If your organization doesn't use Pig, I would say, if you want to just educate yourself in what it's like to use a programming language for data science, I'd suggest Python instead. And then finally, if you're the kind of person, who likes to explore, the latest in the open source community, certainly Spark is a system that you should be playing with. And Spark is based on a language called Scala, which is a functional programming language. And so, as in using Python, I think here, you're forced to think a little bit more like a programmer. in learning Scala. But I think that the Spark and the MLlib, are quite interesting tools for doing modeling at scale. And furthermore, I expect to see a huge investment in those tools over the next few years, so they will probably evolve very rapidly. And so you'd be well served, I think, to at least play with those.
Okay, very good. The next question actually is a request that you expand a little bit on slide 32. If you want, I can push that slide back to the audience. Regarding sort of Amazon EMR, the question is, EMR quickly provisions clusters of varying sizes that include many features. Does that make sense to you?
Sure. Many of the features on the slide?
Yeah, I don't know. The request is just to expand a little more detail, and then the example is Amazon EMR quickly provisions clusters of varying sizes that include many features.
Well,
if that doesn't make sense,
I suspect if you go, I have a feeling that perhaps, this is a question about the previous slide, where, we say, hey, Hadoop is set up for you, and it says, hey, Amazon, no. And my comment on that would be, I go back and forth on that particular box. I think that if you're allocating a 5-node cluster with EMR, it works. If you're allocating a 500 or 1,000 node cluster with EMR, it works sometimes. And look, EMR is great. It's a lot better than going to apache.org, downloading some tar files, and trying to set up a cluster. So, I think that EMR is a wonderful tool for playing with Hadoop and with the MapReduce in particular. But in terms of having an always-on persistent Hadoop cluster at scale, I think it falls a little short from what you get from any number of Hadoop as a service providers, of which Altoscale is just one.
Okay, well, thanks for being able to figure that out. I'm sorry I wasn't better at finding out on my own. The next question is, what are the best breed tools for data integration of files that are in the terabyte sizes? And would Altiscale deal with data integration given that porting big data could be a deterrent?
I think it was data ingestion, right?
Yes, I apologize. You're correct. Data ingestion. Sorry about that.
Yeah, so there are two parts to data ingestion. One of them is transporting the data, getting it near your Hadoop cluster or on the Hadoop cluster, and then the second part is the ETL that we've already discussed. So, I'm presuming the question here is more around that transport part. I think that does more properly fall outside of the scope of data scientists, but it's important, right? If you don't have your data, then you're stuck. And again, a lot of times as a data scientist, there's interesting data out there that hasn't been ingested yet, and you need to be an advocate. Say, hey, no, we really got to get that data. So it's useful to be familiar with how that works. There's two different models of moving data. There's more of a periodic file transfer, which is generally called FTP, although people don't necessarily use FTP specifically for that. And then there's more of a streaming approach where data comes in a record at a time, and then there are tools that are more SQL-oriented. So you might call this extraction tools, which can either are closer to the FTP in terms of the actual transport, but they do involve executing complex queries on some kind of source database system. So those are the three overall models. Some of the tools that are out there are, say, Kafka and Flume, that are for the more streaming-oriented delivery. And at Altiscale, for example, we support both of those. There's a tool called Scoop, which does the extraction. And quite honestly, while it's theoretically possible to use Scoop at Altiscale, typically, in our experience, it's better to run the SQL queries closer to the source data and then send it as a flat file to us. And I think that would be true wherever you have your Hadoop cluster in a data center that's distant from the source database. So those are some of the tools that are out there. I think part of the question as well is around the practicality of moving data around the internet and perhaps into and out of the cloud. My experiences there are, even, if you've got hundreds of terabytes, even a terabyte, and you start to break that down into, hey, how much data per day, how much data per hour is getting moved? If you've got 100 terabytes, and a 2-year retention period, it turns out to be a relatively modest amount of data. That is to say, data movement, even for reasonably large data set sizes, is not that much of an issue. Even when you really need to, I think the key point there is you need to think about, hey, what gets moved every day? Not versus, hey, there's a petabyte. How do I move a petabyte in one day? Because nobody does that. And the world is increasingly distributed. Whether you're doing Hadoop in the cloud or doing Hadoop on-prem, the sources of data are all over the place. Data has to get moved. There's no avoiding this movement problem. But like I said, the good news is, a little bit of data every hour multiplied by 2 years, that adds up to a lot of data. Now, if you have tens of petabytes or hundreds of petabytes, at that scale, you start to have to engineer those data flows, very carefully. You're at that Yahoo and Google scale of engineering. Obviously, those problems can be solved, but honestly, very few organizations do operate at that scale.
Okay, well, that's going to have to be our last question. We're unfortunately out of time. Raymie, great, thoughtful responses to some really good questions. So thanks to our audience for all the questions that came in. We had a lot that came in that we just don't have time to answer, but rest assured these questions are being sent to Raymie and the folks at Altiscale, and they will respond to you in short order. I just have a couple of quick announcements to make. To please mark your calendars for January 20th and our next Data Science Central webinar, Data as the New Oil Producing Value in Oil and Gas Industry, sponsored by Pivotal. I just want to thank Raymie and Altiscale for sponsoring today's event. It's been a pleasure having you guys participate with us today, and we'll look forward to seeing you all again on January 20th. Good day.